Now that we've taken a look at the goals of the class and some of the steps that we'll be taking over the next 8 weeks to reach that awesome end result, let's start taking a look at our fracturing techniques. Now first, we're going to go over the Voronoi fracture. This was the industry standard fracture technique for quite some time. Nowadays, Booleans are often preferred, but Voronoi fractures still have their place and are still widely used. Now this fracture technique is based on using some scattered points to determine where the fracture lines will be. So with this basic object, just a very thin grid here, I've scattered some points on it, and the Voronoi algorithm will determine the midpoints between our scattered points and place some cut lines there. Now setting up these fractures is pretty quick and easy to do. All you have to do is, well, let's start by taking a new box here. Let's make this one a bit more 3D than that super thin one we just took a look at. Let's maybe make it 20 by 10 by 20 and view that. Let's lift it up a little bit. Alright, and we'll start by scattering some points on the surface of that box. Let's start with a very low number first. Let's just drop in that scatter node, connect the box to it, and this will default to 1000 points on that force total count number here. Let's turn that down to just maybe 10 points, and if we put the template view on our box, you can see those are just on that outer surface of that geometry. And to run our first Voronoi fracture, you can just drop in the Voronoi fracture node, connect the geometry to be fractured to the first input, the scatter points in the second, and view that result. You can see from the wireframe and shaded, if we template our scatter points, it's, as we've seen before, approximated those cut lines in between all of those points. Let's do an exploded view to get a better look at this. Now you can see that because all of the points were scattered on the outside of the geometry, we don't really have any interior pieces in the middle of the object there. Now if we want some more interior pieces, we'll have to scatter some points inside the geometry. One of the quick and easy ways to do that is to create a VDB from polygons node, like so, connect the box to it, and by default that will create an SDF volume which doesn't look that much different than the original box, and we'll talk more about SDF volumes later, but for now let's uncheck that distance VDB. It's essentially another way to refer to an SDF volume, and turn on that fog VDB, which if you've used normal Houdini volumes before, this should look more familiar to you. So that'll just create a density volume filled with values of 1 all throughout. So now that we've got that volumetric representation, if we do a scatter within that, pipe the volume into it, and once again, this will create 1000 by default, and we don't need that many. Let's turn this down to 100. And you'll notice that if you're very picky about this, you may notice that these points are kind of biased toward the edges of the box here. And that's not necessarily a problem. It's just something to be aware of when doing a volume scatter like this. I often like to turn off the relax option to fix that. You can see if you turn off this relax here, then they're kind of more randomly distributed throughout that space. And it's a bit uneven in terms of the distribution here. You can see that there are more points in this section here and fewer up in this corner. And the relax tries to kind of even out that distribution. But in the process, yeah, it can kind of, as you can see, flatten them out to the edges a bit. You can also play around with the number of relax iterations for something halfway in between the two extremes. Now, if we wire those new scatter points into the Voronoi fracture, and view that exploded view output, you'll see now we have some inside pieces generated within that geometry, not just edge pieces that extend all the way inwards. Now this is a pretty interesting result here. We could get some cool effects out of, doing a rigid body sim on these Voronoi pieces, but you can see they look pretty regular and geometric. And there are some things we can do to reduce that on these Voronoi shapes. If you're familiar with the old version of the Voronoi tool, this Houdini node used to have some interior detail built into the Voronoi fracture itself. They've since split that out into a separate SOP. I assume the idea is that it's a bit more of a flexible workflow and that you can then use other types of fracturing and then run the same interior detail regardless of which original fracture technique you use. But I will be perfectly honest, I don't really use this RBD interior detail node myself. I always just do more detailed Boolean fractures that we will get into shortly. But it's still good to be aware of the option here. And if you connect our exploded view results to that interior detail node, maybe we'll just do this with a few less pieces just for the sake of the demo. Let's turn that down to 20. You can see it's adding a lot of resolution on those inside faces. Right now that's pretty flat, but you can increase the noise amplitude to create some more interesting shapes there. But by default, we're getting some kind of weird behavior here. You can see the noise appearing in some sections, but others still look quite flat. And all of this noise detail is constrained by some of these options at the bottom of that RBD interior detail parameter set. Now the main purpose of this parameter set here is to control the noise amplitude based on depth within the surface. If you were to have the interior noise go all the way to the edge, then those interior faces and points might pop outside of the geometry, and that'll make the exterior look pretty messed up when it's supposed to be nicely intact. So you can go back to that RBD interior detail and turn on Visualize Noise Scale to help see where that displacement is being added. And we can try turning off clamp displacement amount to depth, and we can use this depth/noise bias to further compress the amount of noise allowed at a given depth, or to restrict that less as we bring that bias up. But you can see we're still getting some strange results, and this just looks like some pretty crunchy detail. And I find this very difficult to art direct a look that I like. So anytime that I want that level of detail, I'll just use Boolean fractures. So you can feel free to play around with this if you'd like. Just know that I don't find myself ever using this in production nowadays.